Like as soon as my other one broke, I ordered this.
Dude, I give you if you guys
There it
watch
is.
it. I can only watch it on my Xbox though. My computer doesn't have the file the format or whatever to run it. It's a different like audio video file.
Okay, well, I hope everyone's been keeping up with their homework. We're going to move on today to chapter 7, section 4, and we're going to do 7.5, and we're going to start 8.1. Now, I know that sounds like a lot, but this 7.4 and 7.5, two concepts, and that's it. There's no like integration by all these different methods. I mean, it's very straightforward. Two formulas really is all it is. And then we move on to chapter 8, all right? So, 7.4, arc length. So, if you go back and you think about all the things that we've done so far with these integrals, if we review quickly, we could find, the area between two curves, right? We could take that, we could extend that area out on an infinite interval, right? Improper integral, like make it go forever. Sometimes the integral converged, sometimes it diverged. We could have areas where we have like a vertical asymptote like this, and we could try and find the area in here. Again, sometimes it converged, sometimes it diverged, all right? All this ring a bell? We took something like this, we rotated that around, let's say, the x-axis, and we found some volume, right? Some shape, and we find its volume. We could rotate it around the y-axis. We could rotate it around different lines, right? Vertical and horizontal lines. We never did a diagonal, though. It's possible. We just don't usually cover that in a class like this. So we had areas, volumes of revolution. When we did the volumes, there were two methods. There was washers and shells. Washers requires that your rectangle you draw is perpendicular to your axis of rotation. Shells parallel, right? Rectangle is parallel to the axis of rotation. And then we did these weird things where, remember the very end of last class, where you took an object and said the base looks like this. Perpendicular cross sections are squares, or they're circles, or they're triangles, or something like that, right? Yes? Okay. So now today we have a new concept, arc length. And you would think that this concept would have come before all this other stuff, because the idea is pretty simple. If I take a curve, so this is like back in Cal 1, if you just take a curve and you go, let's say, from some point A to some point B on the x, then what if we take that curve off the sheet of paper, imagine it's a string, and straighten it out tight, right? And measure L, the length of that curve, right? Then that would be like, if this was a little bug crawling on this whiteboard, then that L would be the total distance it would have traveled, right? Linear distance. And that's what we are attempting to do in this section. So just like everything that I had on the board before this, everything we did relied on this idea of like a Riemann sum, right? We found a formula that represented what it was we were trying to find, and then added them all up, and then that created an infinite sum integral, and we were done. We want to do the same exact concept with this. We want to somehow cut this curve into an infinite number of little pieces, and then add up the lengths of each of those pieces. Got it? So to do this, what we will do is imagine taking a small, infinitesimally small, zoom in picture of that little segment. And let's blow that up, and let's look at that one little segment over here. And it would just look like, if it was blown up, it would look like that, right? So that's my blown up version of that little piece, yes? Got it? Now, I know that if I drop perpendicular down straight from this corner down, and I go straight across like this, that I would create a right triangle. And the length of this black curve is pretty darn close to the length of the hypotenuse of that triangle, isn't it?
Yeah.
And if I zoom in more and more and more, what happens is it gets almost straight, right?
Yeah.
Now we're always going to have a slight error, right, in the difference between the red hypotenuse and the black curve. But again, if we keep on cutting it smaller and smaller and smaller, little tiny infinitesimal triangles, then that error becomes negligible and we should get the true length, yeah? So it'd be great if we could approximate the black with the red. So can we come up with a formula for this red hypotenuse? Well, that's gonna rely on whether or not we know these two sides of the triangle, right? So the question is, do we? So does everyone see that I could have drawn this picture? Back when we were doing areas, we came up with this rectangle, didn't we? And that rectangle, we said it was going to have an infinitesimally small width to it. That was dx. Does it make sense to you that this right here would be dx then? Yes? And then if this dx represents your infinitesimal change in x, then this distance should be your infinitesimal change in y, shouldn't it? So dy. And by the Pythagorean, right, you get a squared plus b squared is c squared. So this, let's call this L. Let's call it, I'll call it little l, okay? Little l squared is dx squared plus dy squared. Do we agree? And if I solve for L, then square root on both sides, we get L is equal to the square root of dx squared plus dy squared. Agreed? That's the length, approximately the length of that little infinitesimal hypotenuse. And all I need to do is add them all up, right? So now the integral. So I'm going to set up an integral now. This integral is going to vary. Like, remember, we're moving, just like we moved the rectangles across here, we went from A to B. We're going to move these little segments across. So it's still going to go from A to B. But what is the formula that we are going to use?
The square root.
This right here, right? And when we look at this formula, we're going to have a pretty major issue. We've never seen anything like that before. Every formula that we've had before, right? If you go back and you look at like the area under a curve was integral a to b, it was f of x dx, width of the rectangle, height of the rectangle, right? Or when we did the volume of revolution, we had like pi, then it was the function squared dx, and that had to do with the fact that we came up with the formula for the washer. All of these had the right format, dx, right? They all had that dx out there. This one, the dx is trapped, isn't it? And we even knew with integration to never trap your d whatever, right? Not only that, we have dy. And we've never had dy and dx in there at the same time. Agreed? Okay, so there is a workaround that I'm going to show you. Let's just remember that with this picture, we are assuming that this black curve is y is some function of x. Do you agree?
Yes.
And from Cal 1, if I asked you to take the derivative here, right, then you would write, I'm going to erase this. You would write y prime equals f prime of x. Yeah? Now, another way you could write y prime is using Leibniz notation, which is where you get the dy dx, right? So this is the same as saying dy dx equals f prime of x. Yeah? And then if I multiply both sides by the differential, dy is equal to f prime of x dx, isn't it? Now, what this is going to do is it's going to allow me to go back into my formula, which I'm kind of stuck on right now, and replace my dy with this. So let's do that. I forgot to put L out here, total length. So the length of the curve is integral from a to b square root dx squared plus, but instead of dy, f prime of x dx quantity squared. Does anybody see what I'm going to be able to do? Factor out a dx. Actually, since I'm squaring this, and this is a product, right? I'm going to square the derivative f prime, and I'm going to square the dx. So they'll both be squared, right? It'll look like this. I'm going to write this it's going to look a little strange, but just tell me if you agree or not. Isn't that the same thing?
Yeah.
Squaring each one. And now do you see there's a dx squared here and a dx squared here? So you can factor out a dx squared from both. And when you factor that dx squared out, I'm going kind of slow here, you're left with 1 plus the derivative of f, I'm going to put that in brackets, squared, right? I don't need this in brackets, but this multiplies back through here, and you get back this, right? Now what can I do with the dx squared? Pull it out of the radical, but take the square root, so it's just the dx by itself, isn't it? And I'm going to pop it to the back. That look better to you? Does it look a little bit more like things we've seen? I mean, at least we have a dx at the back, right? That's what we've seen before. This is what we have to compute in order to be able to find the length of the curve and integrate that. Pardon? 1 plus something. Now, what is this right here? That's the derivative of the curve function, right? So what you're going to do to find the length of a curve, you must be able to integrate the square root of 1 plus the derivative of the function squared. If you can integrate this, you can find the length of the curve. Got it?
So if we forget how to take derivatives,
yeah, that's not really going to be the challenge of this, though. The challenge of this is going to be whether or not you can actually integrate this. And because this looks pretty complicated, or it can get complicated, we have to be very selective as people introducing you to this topic. We have to be very selective about the function we pick. If I just pick some arbitrary function right now and try and find its arc length, most likely I'm not going to be able to do it. I'm going to get an integral I can't do by hand. So then I'd have to go to a computer to do it or something like that. So you'll notice that as I work through the first example, the curve that we pick, this stuff in here is going to be real nice. Okay? Understand? That's it. That's the formula. Now, I'm going to put a little asterisk here. There is a way to handle a function of y instead of a function of x, and the formula changes a little bit. I'm not going to do that. We're looking at 7.4 and 7.5. We're looking at just basic idea that we can find arc lengths. All right? So we will only do it for functions of x. First example. Find length of y equals x to the 3/2 on the interval 0, 1. So y equals this, this is a function of x, right? So our f of x here is x to the 3/2. We know what the formula is. You have it written down there, but I'll put it here. We need to be able to do this, right? So I'm going to need to know what the derivative is, right? I'm going to need to be able to square it, and then I can put it in here. So let's go ahead and take the derivative now. The derivative of this, 3/2 x to the 1/2. So this is, I'm just doing work over here. I'll come back and do the integral in a minute. And then how about we go ahead and square it now, just to see what would happen if I square that thing. So 9/4 x x to the 1, right?
Yeah, to the first.
Because this is a square root, and you're squaring it. So you square a square root, you just get the x. You okay?
Yeah.
Sure? Yes? Okay. That's it. That's what this piece is going to be. So I think I'm ready to set up the arc length. The length of this should be the integral from, now do we have a restriction on our x values? 0 to 1. It's given, right? We're going from 0 to 1. And we're going to do square root of 1 plus 9/4 x dx. And that's about as simple as any arc length problem will ever be, because that's a pretty basic integral. How do we do that integration? You could just let u be everything under the root, right? The derivative of that is 9/4 dx. You don't have 9/4, so you could just scale this out, make it 4/9. du is dx. And then all of this integral. See, I'm not going to do all the limits of integration and stuff yet. I'm just doing the work of integrating right now. This becomes integral square root of u, right? And then dx becomes 4/9 du, so like that. Do you all follow me? And what is the antiderivative of the square root of u?
Or 2/3.
2/3 u to the 3/2. So that's what the antiderivative, plus c, but we don't need the c because we're going to come back and do 0 and 1 in there. Anything clean up here? Nothing reduces, right? So 8/27 u to the 3/2. 8/27 u to the 3/2. So I think I'm ready to go ahead and do this now. The length of the arc becomes the antiderivative of this, which we just said is 8/27 u to the 3/2, but u was 1 plus 9/4 x to the 3/2. Right, that's our antiderivative. Evaluated 0 and 1. Plug in. So let's plug in. This is going to be fun. Okay, 1 goes in here. That's just 9/4. 9/4 plus 1. 13/4. So let me just write this out. I'm going to have two things. Right? Yes, the 0 will have to go in. Yeah, because it will actually turn into something. So 1 goes into here. You said I've got the 8/27 out front. You said that was, what, 13/4 to the 3/2. And then over here, when you plug in 0, this goes away, but you still have 1. 1 to any power, still 1, so you just have 8/27 here. That would be the exact form of the answer. Okay? And you could get the decimal by plugging things in and getting a decimal.
That would be good.
That would be good, yeah. But do we want to know what that is as a number, or do we care, or no? No? Okay. All right. Understand? All right. Let's do another one. No, everyone keeps asking that, and that's my college algebra book. It's not ultimately my choice, but okay. How about, let's try this one. Find the length of y equals x to the 4th over 16 plus 1 over 2x squared, with 1 being less than or equal to x being less than or equal to 2. Now remember what I said. Because this arc length, the formula, the square root of the 1 plus the derivative squared, can be ugly, we have to be very selective on how we choose the function so that you can integrate it. This looks bad because it had to be picked so that you could handle it. If you just pick some function at random, you're most likely in trouble. All right, you're not going to be able to do it. All right, I like this problem. And I like it because of the algebra that's going to occur. All right? So you'll see in a little while. Find the length. So this is f of x, right? So I'm going to need to know what is the derivative of this. 1/4 x cubed. So that's really like 1/16 x to the 4th. 4 pops out, power comes down. This one, remember, before you take the derivative, remember that's the same as 1/2 x to the negative 2, right?
Right.
That's what that is. So when you take the derivative of that, you're going to get negative x to the negative 3. Do you all agree? No questions? Now, I'm just going to write this a different way, even though you don't have to do this. I just want you to see, make sure we're all clear that this is the same thing, right? What are we supposed to do with that? Square it. Let's do that now, okay? Let's get that out of the way now. Let's square this. Ooh, how do you want to square that? You have to FOIL it out. You have to expand it, right? You don't just square each term. That's a big, big, big bad thing, right? That's what I have to do, right? So let's do the first multiplication. This times this, which is 1/16 x to the 6th here and here. 1/4 x cubed times. That's what I'm doing, right? Negative 1/4. The x cubes will cancel, won't they? So negative 1/4. What about the inner one? Negative 1/4 again. And the outer multiplication? Positive, right? 1 over x to the 6th. Or x to the negative 6. You can do it either way. I'm just going to leave it like that. Negative 1/4 minus 1/4 is negative 1/2. So I'm cleaning this up as much as possible. 1/16 x to the 6th. Really doesn't matter what order we put these in. There's your derivative squared, right? Now we're ready to try and put this into the arc length formula. No questions though? The length of this should be equal to the integral from 1 to 2, square root of 1 plus this, 1/16 x to the 6th minus a half plus 1 over x to the 6th dx. Now that probably looks horrific to you, right? And that's why I said that I like this problem, because the algebra that's about to happen, all right? And you have to be paying attention to this when you're trying a problem like this. You have to be, I guess, aware that this is what you need to do, all right? We're going to try and clean this up, all right? So do you see anything I can do so far?
The 1/2 and the 1.
Yeah, I can put 1, take away a half, that's a half, all right? Let's see if anyone has any instinctual things going on here where they just feel like doing something, just they can't explain why, they just want to.
Won't the x to the 6th power cancel out?
Want what?
No.
That's what we have? How do you mean? Nope, because it's addition between these. You can't square root them individually. You can't square root them each individually. Just remember, look, if you ever run into an issue where you're like, can I do that? Just take something that you know for sure. Can you do the square root of each one of those?
Yes.
Individually.
Yes.
So that you're telling me that this is the square root of 4 plus the square root of 9? That the answer to that's 5? Square root of 13 is not 5, right? You can't do that. So we should not be able to do that here, right? Do you understand why I put that up there? Just to show you, like, algebraically, you can't do that. If it's multiplication, can you?
Yes.
Square root of 4, 2. Square root of 9, 3. Is that 6? Okay, well, what's 4 times 9? 36. Square root of 36 is 6. So it works, right, with multiplication. I heard someone say something.
Plot an x to the 6th out of the last two.
Well, I have an x6 on the top, and here there's one on the bottom. So if I factor it out,
Could you put everything together?
oh, to negative 12.
The x to the 6th out of the root.
Yeah, we might actually be able to do that, but I think that still might lead us further away, which in math, that happens a lot. You're trying to do a problem, you're not breaking any rules, you're doing all your algebra right, but you're leading yourself off this long path that the answer, you may get to it, but it just, you might get lost in the woods too. That's part of the challenge. So I heard put it together. What do you mean put it together? Common denominator. Let's try common denominator. So if I rewrite this, that x to the 6 is really on top, isn't it?
Yeah.
Like this? What would my common denominator be?
X to the 6th and 16.
16x to the 6th. You have to turn every one of those into a 16x to the 6th on the bottom. So what do I have to multiply the top and bottom by here to get a 16x to the 6th on the bottom? 8x to the 6th on the bottom, 8x to the 6th on the top. What about on the top and bottom here?
X to the 6th.
Just x to the 6th, top and bottom. What about here? 16. Understand? Let's rewrite it. Something good is about to happen. All right, so this is x to the 6th times 1, which is 8x to the 6th, over my common denominator, which was 16x to the 6th, plus this one is what? X to the 12th over 16x to the 6th. And then the last one is 16 over 16x to the 6th dx. Right? Now you can put all the fractions together, which means all the numerators go together. And I'd like for you to write all the numerators out in descending order, highest power of x down. So x to the 12th plus 8x to the 6th plus 16 over, what's my denominator? 16x to the 6th dx. All right, that's fair. Anybody see it? How do you mean?
You can do square roots individually, right?
Nope, still can't.
Top and bottom?
You could do top and bottom separately. You can do square root top and bottom. This is okay. This is a legitimate algebraic move. That's okay. Before I do that, though, I heard factor. Factor how? What do you mean? How do you mean?
It's x squared to the third, and x squared to the third? Oh, no,
X to the 6th plus 4 squared is what the top is. You have to recognize the top, this trinomial, as a binomial squared. Do y'all see that this is this? It's like if I wrote down over here x squared plus 8x plus 16, I would trust everyone in here would be able to factor that as x plus 4 squared, right? But instead of 12, we have, instead of 2, we have 12, and instead of x, we have 6. So this is a quadratic type, isn't it? And we can factor those sometimes. In this case, yes. Why? Because they made sure we could when they made the problem. Questions? Okay, so this just becomes now integral 1 to 2. Now let's split it into 2 square roots. What's the square root of something squared? It just goes away, so we just get x to the 6th plus 4 on top, right? Over square root of the bottom, 4x to the 3rd. That's much better. What can you do with that? What can I do? You could do long division, but it's more than you need. Sometimes you go so far into something that you forget the basic stuff. Not even that. Even easier. Split it up. Okay, split it up into 2 fractions. One denominator, 2, split into 2. So you do x to the 6th over this. So x to the 6th over 4x cubed. See, this is like one of the first problems we ever did with integration, right? The power rule. Split it up into 2 fractions, and then clean that up. That first one is, can I rewrite this first one as 1/4 x cubed?
Yep.
And this one I can rewrite as 1 over x cubed or x to the negative 3, however I want, right? I'm about to integrate it. That's why I'm going to leave it as that. And now, just power rule. So we get 1/16 x to the 4th.
Just the original problem.
Is it?
Negative 2, or 1 over 4, 1 half.
1/2
1 half
x to the.
negative 2.
Is it the original?
Yeah.
That's interesting.
You just wrote it differently. It was x to the 4th over 16
It's just a minus sign.
Oh, it's a minus sign, so it's close. That's completely coincidental. Don't get to the test and be like, I know the answer is the same as the original function, just with a minus. No. All right, I'll write one more line. 1/16 x to the 4th minus 1 over 2x squared. Evaluate 1 and 2.
Plug in.
Now plug in. So let's plug in 2. When we plug in 2, we get something.
16. 16 over 16.
So 2 goes in here, we get, what? 16 over 16, so 1. 2 here.
4 times 2 is 8, so 1/8.
1/8. So is 1 minus an eighth? 7/8. Yes?
Yes.
7/8 minus, now plug in 1. 1/16 minus a half. What is 1/16 minus a half?
8/16.
This right here turns into 8/16, right? So you subtract and you get what, 7/16? So this is 7/8 minus negative 7/16, so plus 7/16.
Oh, yeah.
21/16.
What was that? You sure? You got it? Okay. Which is 21/16. Get a common denominator. Okay.
Most of these are fractions, though, right?
What's that?
Like, even in the homework, most of them are fractions. The actual.
Answers or?
Yeah, the answers. Oh, the homework for the other one.
Yeah, I don't know. 27.
Yeah, they
Okay, we good? Yeah? All right, that's it. That's all we're going to talk about arc length, all right? Now, the problems that I would recommend you do for homework, I'm not going to give you a bunch, just maybe like 2. This is a topic that is not always covered in detail in a course like this, all right?
Yeah, why though? Why?
Just we have so much material that, you know, we could spend a lot of time on this, but we choose not to. This page 391, maybe look at 7, 9, maybe 15.
Is it considered like one of the less important ones to cover, or what?
I mean, it's definitely less important than like techniques of integration. Like,
Yeah.
you know, it's a result, right? The volumes I think are focused on a little more because volumes, like you have to kind of visualize and come up with the formula. You know, the solids of revolution, like where's my axis of revolution? Where's that outer radius, inner radius? That's a little more like in-depth, like deep thinking. Then this is more like a formula. Apply the formula. That's all that is. All right. I'm just curious real quick. I see if I can make this real quick or not. If I give you a circle, and I tell you it has a radius of A, what is the circumference of this circle? Well, let's go R, because you like R for radius. What's the circumference of a circle? 2 pi r. Says who?
Everyone else is fine.
Alexis, that's it? Okay. So where does this come from? Well, check this out. Isn't this x squared plus y squared equals r squared? That's the equation of a circle. If I'm going to focus right now my attention on the upper half of this circle, right? Then I could solve this equation for y. And if I solve that for y, I get y is equal to square root r squared minus x squared. Do you agree?
Yes.
And I would technically need plus or minus, but if I'm just looking at the top half, it's just the plus, right? The minus draws the bottom half. What if I asked you for the arc length of this? Wouldn't that be half the circumference?
Yeah.
So divide
Yes?
by that.
Right? So what I'm going to ask us right now is what is this blue length? What is the blue length? This is the function, right? What is the derivative of this function? Remember, r is a constant.
It's changeable.
Okay, so
1 over 2 root r
2 root
squared minus x squared times 2r.
negative
Oh,
2x.
yeah.
Remember, r squared is a
Oh,
constant.
yeah, okay. So it's
0, derivative of this, negative 2x. Do you all agree that's a derivative? which is that, negative x over square root r squared minus x squared. Yeah? Now, in arc length formula, I also need to square that, don't I? So if I take this, what I'm doing is I'm wondering right now, can we prove right now that the circumference of a circle is 2 pi r? Can we? All right, we're about to see if we can. Square top and bottom. X squared over r squared minus x squared. Yeah? That's it? That's the derivative squared? Okay, now let's go to the formula for the arc length of the curve. The formula is that the length of that blue piece is going to be the integral from,
1 to 1.
how far are we going out? The radius, right? From the negative radius to the positive radius. Okay, so I'm going to cheat a little bit here. Why don't we do this? Why don't we just find the length of that and multiply it by 4, right? So that way we can go from 0 to r instead of negative r to r. Is that fair with you?
Yeah.
Fair? Yes? 0 to r. I'll multiply by 4 at the end. And then I'm going to do square root of 1 plus this thing, right? Any ideas on what to do with this? What did we do in the last problem? Common denominator. So what's my common denominator going to be? R squared minus x squared, up on top, r squared minus x squared.
X squared cancels.
So you get 0 to r. What happens up here? R squared minus x squared plus x squared. R squared, bottom. Squared minus x squared. Dx. I forgot the dx, sorry. And now can you do the square root top and bottom? Okay. So let's do square root top and bottom. When I do the square root of the top, what do I get? R. R is a constant, right? Pop it out. R integral 0 to r. What's left? 1 over square root r squared minus x squared dx.
That's a trig sub.
Trig sub.
Yeah.
Very good. Now, but it's also a formula. Someone look on the back of their formula sheets and give me the formula that had constant 1 over the square root of constant squared minus variable squared. Now we could do the trig sub. We could, but I'm going to go to the formulas instead. 1 over square. It's the one that's 1 over square root of a squared minus u squared. Is it over here? Right there. 16. Formula 16. See, r is the a. So what is it? Formula 16.
Inverse sine.
Arc sine, that's it? Nothing in front of it?
Yeah, nothing in front of it.
Arc sine,
U over A.
u over a. What's u for us? Nope. X. X over a, which is r for us, right? That's the antiderivative? Okay, and then we're evaluating that 0 to r. Understand? Now remember, the r popped out, right? Here's the formula. Here's the r that popped out. Here's the antiderivative of this according to formula 16. Here's our limits of integration. Plug in 1. Is that a question? No?
Are we waiting for the 4, or do we just want to put?
At the very end, okay? So plug in r right now. R over, for x, right? R over r is 1. Arc sine of 1? 90 degrees, which we'll write in radians. Pi over 2. So here's what we have. We have r times, you said this was pi over 2?
Yes.
Pi over 2, that's it, minus, plug in 0.
0.
0 over r is 0. Arc sine of 0? 0. So that's just gone, right? So what's our answer? R times pi over 2. So 1/2 pi r. Then multiply that times 4. 2 pi r. Right? So that was, remember, that was just the top. I had cheated. I said, let's just go and do this piece. So we found that that length right there is 1/2 pi r. Multiply 4 of them, and you get 2 pi r. It's kind of cool, huh? Okay. It would have been more fun to not use the formula and actually do the trig sub. I think that would have been more like we're bringing everything together. We just don't have time. 7.5. Area of surface of revolution. So remember what we've done before when we were talking about volumes of solids of revolution, right? What we did was we took a curve and we wrapped it, let's say, around the x-axis, right? So we said, let's wrap this thing around the x-axis. And when we did that, we would get this solid that would, look like that. And we found V, right? Volume. Check. We know how to do that, right? Instead of asking what the volume of this is, what if we were asking what is the area of the surface of this? In other words, like the outside of it is area, as opposed to filling it up with something which would be volume, right? So is everyone comfortable with that? When you measure the length of something, length, it's just your units, like, for example, feet, right? If you're going to measure area, you need 2 dimensions, right? It's your unit squared, so like feet squared. And then if you want to do volume, that's a 3-dimensional thing, so unit cubed. Feet cubed, cubic feet. Yes? We're all comfortable with that, hopefully? So these are completely different concepts, right? We know how to find the volume, which would be what we would need to fill this thing up. Instead, let's figure out how much paint we would need to paint its surface, to cover its surface. Understand? All right, so just like everything before, we're going to come up with a formula. We're going to find out what it is, and then we're going to add them all up, and it's going to turn into an integral. Got it? So let me show you how we can do this. Let's go in here, back to this picture, A to B, like that. Let's zoom into a little piece again. That little piece that we have there, right? We can find its length, no problem. We're okay with that, right? But instead, we're wrapping this little sliver, we're wrapping it around the x-axis, right? So let's do that. Let's wrap this little sliver around the x-axis. If I wrap that around, what am I going to get? Won't it look like a disc, right? Like a coin? But here's the difference. We don't care about the volume of this. What do we care about? We care, hold on, I need to start this over. So if I wrap that little piece around, I'm now looking at something that looks more like a rubber band, okay? And I'm looking at the surface area of the rubber band, as opposed to looking at this as a solid disc. Understand the difference? So what would the surface area of that rubber band be? Why don't we cut it open and lay it flat? We've done that before, right? Just come in here with some imaginary scissors, clip it right there, just one edge, lay it out flat. It would look something like this. Right? Can you tell me what the area of this would be? Length times width, right? So you're tempted to use dx, right? You're tempted to use dx to measure this, right? But is this actually dx? Isn't it this little length right here? And what is that little length? Isn't that arc length? Isn't that the little arc length?
Yeah.
Right? This little length right here is actually the arc length, not dx.
So we'd have to use the other formula to get that.
So this edge right here is actually the square root of 1 plus the derivative squared. Because here's the thing, it's not straight, it's a little curved. And then this length right here, what is that?
That's the f of x.
Is it f of x?
Because that's the formula away from the origin, right?
F of x is this length.
Yeah.
Isn't f of x only from here to here?
It's 2f of x.
Is it 2f of x?
There's 4.
Remember what we did? We cut this and we laid it open. So isn't this entire edge the circumference of this rubber band? Isn't it? Look at that rubber band from the side, right? From this direction. It's a circle, isn't it? It's 2 pi r, which r, it's not r, it's, you said 2 pi f of x?
Yeah.
I didn't hear you. Sorry. That's it. Area is this times this. The area is this times this. Got it? Integral, add them up. So, what? Why?
Out of all that.
Okay, so the area, I'm going to say area to represent surface area, is equal to integral a to b. This should look familiar. I left some spaces in there on purpose. Add one thing over here. This right here, dx. This right here needed to have the dx on it, sorry. So we need to multiply this times 2 pi times f of x, right? 2 pi is a constant. So 2 pi f, not prime, f of x times, there it is. So everything that's underlined in red here is the only thing different between this formula and the arc length formula, right? The arc length formula is exactly this formula with these two pieces taken out. That's arc length. Add that in, that's surface area. Okay? Now I'm just wondering how, I almost said something really bad. I'm glad I didn't say that. Wow. No, I can't say it. I turn off the mic, yeah. No, I can't even say it even off the mic. I can't believe I almost did, though. Yeah. All right, how about this? Let's take, I want to do one example, all right? Rotate one arc of sine about the x-axis. What is the surface area?
So we're only using 0 and pi as a restriction.
Well, yeah, what do we mean by one arc? So if you look at the sine curve,
Just one arm.
you know, their sine goes in both directions. So we're only going to focus on taking one of these arcs, which is going to be this. We can take any of them, right? But I think that's the most natural one to take. And rotate it around the x-axis. And you're going to get something that looks something like a football, right? And you're going to find the surface area, not the volume, right? Surface area. So what's the function we're going to use here? Sine x. I'm going to need its derivative. That's nice. I'm going to need its derivative squared. There you go. Okay? That good? And now I'm going to go into the formula. The area should be 2 pi integral. Now what's my range here? 0 to pi, because one arc is going to occur between 0 and pi. So integral from 0 to pi of the function itself, sine x, times the square root of 1 plus cosine squared x dx. No, if it was 1 minus. Careful, it's 1 plus, right?
Can you substitute it?
You can like put it in there and it become like an identity.
Put the sign in there?
Yeah.
You could. Yeah, you could do that. But you could also just do a basic u sub.
Yeah.
What would a basic u sub be here?
U equals sine.
U is cosine. Right? What's the derivative of that? Negative sine x. dx, we're off by a sign, aren't we? So I could rewrite that integral with a negative outside, negative 2 pi integral, and then in there square root 1 plus u squared d u. How would you do that? There's a formula for that, I believe. See if it's on your formula sheets. If not, what would you use? Trig sub again. Let's see, who has their formula sheets? I think it's on there. Formula 21?
Remember how the original formula?
It's 21. That's ugly. It's formula 21. So someone's going to read off to me formula 21. Which here, let me give it to me. Okay. All right. So I'm going to read off formula 21. I'm going to do this integral, but I'm going to put u's in here, right, for the formula. My a here is 1. This is 1 squared. So I'm going to read off formula 21, replacing all my u's with cosine. That will be the antiderivative of this. Do you all agree with that? Okay. So I have this equals negative 2 pi, and then here comes formula 21. U over 2, but that's cosine x over 2, times the square root of a squared plus u squared, which is 1 plus cosine squared x, plus a squared over 2, a is 1, so 1/2, natural log of u, which is cosine x, plus the square root of 1 plus cosine squared x plus c, right? But we're evaluating 0 pi, right? And pardon? We did. Yeah, we did the answer.
Be your test question, like something like that.
I just grabbed this out of the book. Yeah. This is number 9. This is number 9 out of the book. Except they use sine of pi x as their curve, so theirs was even a little more.